We saw that we need to consider complex numbers for our choice of the n or two endpoints where we evaluate the polynomial a of x. Here I'll give a brief review of the relevant concepts regarding complex numbers. Some of you may get a bit scared at the use of complex numbers, but the mathematics involved is fairly simple, so don't get intimidated at all. And the final algorithm that we get is very simple and very beautiful. We have a complex number z, which is a plus bi. A is the real part and b is the imaginary part. It's often convenient to look at complex numbers in the complex plane. In the complex plane, one of the axes corresponds to the real component, and one of the axes corresponds to the imaginary component. So for this number a plus bi, we look at a in the real axis, b in the imaginary axis, and we look at this point ab. This number z corresponds to the point ab in the complex plane. Now there's another way to describe this point, this number z. It's called the polar coordinates. In polar coordinates, we look at the length of this vector from the origin to this point z. Let's call r the length. And we look at this angle, theta. This number z in polar coordinates is r comma theta. Just as we had two representations of a polynomial, either the coefficients or the values, we also have two representations of a complex number, either with the Cartesian coordinates ab or the polar coordinates r theta. Now it turns out that polar coordinates are more convenient for certain operations, such as multiplication. Before we delve into properties of polar coordinates, let's review some basic properties. First off, how do we convert between polar coordinates and complex Cartesian coordinates? Well, if you remember a little bit of trigonometry, you'll recall that a, this length a, is equal to r times cos theta, and this length b is equal to r times sine theta. So this gives us a way to convert between Cartesian coordinates and polar coordinates. Now there's a third way of representing complex numbers. This is given to us by Euler's formula. This gives us a quite compact representation of complex numbers. The basic fact is Euler's formula, which says that cosine theta plus I times sine theta equals exponential of I times theta. Then we can multiply both sides by r, and then we have that this number z, this complex number z, equals r times exponential of I times theta. The basic idea of the proof of this Euler's formula is by looking at the Taylor expansion of exponential function, cosine, and sine function.